Today, we are going to learn how to compare numbers that are written in scientific notation. This can be especially useful, especially when reading science articles or looking at numbers that are bigger, way bigger than we're used to dealing with. So one of the things that is important for this standard is that we're going to tell how many times as big one number is than another. So we need to review a few things that we do with exponent rules and what it means to say how many times as big one number is than another. First, what you do with exponents when you multiply two numbers with the same base is you add them. And this is referring to the big number, or the base is the same, and then you add the exponents. So 2 squared times 2 to the 6th is 2 to the 8th. And I explain how to do that in another video. When you divide two numbers of the same base, it looks kind of like this. And you subtract them, so this equals 2 to the 4th. You can find out how that works in my quotient rule video for exponents. But just know that when you divide two numbers with the same base, you subtract the exponents. When you're trying to find out how many times as big something is than another, what operation do you use? Now let's think about this. Let's say we're talking about my daughter and I, and she is about 30 inches tall and I'm about 60, give or take a few inches, right? This is just for the sake of an example, and we want to figure out how many times as big I am than she is. So hopefully you can tell that I'm twice as tall as she is. So I am 2 times as big. So basically we're trying to figure out, what do you multiply one number by to get the other one? So the operation that you do to find out what that number is, hopefully you can tell what we did with 60 and 30 was we divided them. So you divide the numbers to find out how many times as big one is than the other. Now we're going to use what we know to solve some problems with scientific notation. We should note that what notation it asks us to write the answer in. It's standard notation. So if we have our answer in scientific notation, we have to change it to standard notation. Let's do the first problem. A computer's hard drive holds 8 times 10 to the 7th bytes of information. Jill buys an extra USB drive that holds 3 times 10 to the 6th bytes of information. Which holds more memory, the hard drive or the USB drive, and how many times as much? So we're going to answer the first question, which holds more memory. Both of these are written in scientific notation. And when they're both written in scientific notation, that means that the numbers out front are close enough where they're not going to differ by more than a factor of 10. So we can just look at the exponents to compare. This exponent is 6 and this exponent is 7, so the computer's hard drive is bigger. Now we're going to figure out how many times as much information the computer's hard drive holds. So just like we learned before, to find out how many times as big the computer's hard drive is, we're going to have to divide. But which number should I divide by which? So I want to find out how many times as big the computer hard drive is. So essentially, I'm trying to find what number times 3 times 10 to the 6th times what equals 8 times 10 to the 7th. Now, to find out that number, I need to divide both sides by 3 times 10 to the 6th. So I'm putting my 3 times 10 to the 6th on the bottom and 8 times 10 to the 7th on the top. If it helps, how many times as much, when you say this holds how many times as much as this, the first this should go on the top. So we're going to divide these, and it looks really hard to divide, but it's actually quite simple. Because of the way that fractions work, we can divide our fraction into 2 different parts. The first numbers, and then the second part is the powers of 10. So we can divide the 8 divided by 3 and the 10 to the 7th divided by 8, 10 to the 6th on their own. That's because when we multiply them at the end, we're just going to end up with the same result. Like this is the same as this because you multiply straight across the top when you multiply fractions. 8 divided by 3, you could put that into your calculator, but it equals 2.66666. I'm just going to round it to 2.66. And then 10 to the 7th divided by 10 to the 6th, I subtract the exponents, so that's going to be 1. So it'll be 10 to the 1st. Always remember to keep the base. So now we have 2.66 times 10 to the 1st, but I was asked to put this in standard notation. So the last thing I'm going to do is actually multiply it by 10 to the 1st. So my exponent on that 10 is 1, so I'm only going to move the decimal 1 decimal place, and I know that if it's multiplying by 10, it should get bigger, so I'm going to multiply it to the right. So it's 26.6. Now, what was I answering? Okay, this is how many times as big? So what am I answering? The computer's hard drive was bigger. Okay, so computer's hard drive is 26.6 times as big, or holds 26.6 times as much information as the USB drive. Let's go ahead and do another example. This one is talking about a speck of dust. This one's a little hard. So let's read through the whole thing. A speck of dust in an electron microscope is 1.1 times 10 to the 3rd millimeters wide. The image is 7 times 10 to the 3rd times larger than the actual size. How many millimeters wide is the actual speck of dust? So that's what we're trying to find, is the actual speck of dust. So because I don't know it, I'm going to call it A. The reason why I'm calling it A is because this problem is really, really hard for me to envision. So I'm going to write it as an equation to try and figure out what I should be doing with these numbers. So that's the actual speck of dust. So what was the first measurement? This is what it looks like in an electron microscope. So this is how big the image is. And the image is this many times larger than the actual size. So the actual size is going to be a lot smaller. And hopefully that makes sense, because 10 to the 3rd millimeters is 1,000 millimeters. And if you had a speck of dust that's 1,000 millimeters wide, that is the grossest speck of dust I've ever seen. It's no longer a speck. It's just a straight up dirt clod. So we're going to write a little equation. We want to find out actual speck of dust. And it says that the image, which was this first number, is 7 times 10 to the 3rd times larger. That times tells me that we're going to multiply 7 times 10 to the 3rd times A to get what that looks like in the electron microscope. So we're going to put this one over here. So now I'm going to figure out A by dividing by 7 times 10 to the 3rd on both sides. So it really helps if you remember how to solve equations for these ones, because sometimes it might help you to write an equation to represent the problem. Okay, so we have A equals that. Once again, I'm going to do the numbers without exponents and as one problem, and then the numbers with exponents, and then there's going to be a times in the middle, right? Because we have a times on both the top and bottom. So we could rewrite this as this. I usually don't, because it's like an extra step, but you can write it that way to help you remember that you should multiply those numbers together at the end. So let's figure out what 1.1 divided by 7 equals. Oh, I already had it in my calculator, 0.157. So I'm going to go ahead and write that over here. 0.157. Okay, now we need 10 to the 3rd divided by 10 to the 3rd. You can think of this as in two different ways. We subtract the exponent, so it would be 10 to the 0. But it's also the same number over the same number. Like, those are the same thing. And I always know that equals 1, which actually is 10 to the 0. So this is just times 1, or 0.157. Now I'm going to answer my question with a sentence. I was trying to find how big the actual speck of dust was. So the actual speck of dust. Oh, I need more space than that. Okay. The actual speck of dust is 0.157, and the measurement was millimeters. Millimeters. I almost spelled that with a D. Wide. Right. Now let's go look at this one. This one's a little different, so be careful when you're reading these. See that you're envisioning the problem. A particle of dust has a mass of 7.53 times 10 to the negative 10th kilograms. Hopefully you're seeing that negative and you're thinking, that's going to be a really small number. Which, think about it, a particle of dust does not weigh 1 kilogram. It weighs a tiny, tiny, tiny fraction of a kilogram. And a kilogram is about 2 pounds for my American audience. 2-ish pounds. It's not exactly. I feel like somebody's going to comment and critique me on this one. But it's about 2 pounds. So it wouldn't make sense for a particle of dust to weigh 2 pounds. That's giant. So this is a very, very small measurement. It's going to be a very tiny fraction or a very tiny decimal. Now what we want to find is the weight of 5 billion dust particles. That's a lot. So 5 billion dust particles tells me that I'm taking whatever the weight is of that dust particle, and I'm finding 5 billion of them. And that word "of" gives me the clue that this is multiplication. So I want to find out what 5 billion times 7.53 times 10 to the negative 10th is. And I'm going to use scientific notation. You could use just like plugging in the zeros of a billion, but you may find that you forget a zero. I frequently do. So it's actually a little bit easier to do it with scientific notation. So 5 billion, you could Google search this. What does 5 billion look like? But I know that, so when I'm writing my zeros, the first zeros are ones, tens, hundreds, then thousands, 10,000s, 100,000s. I feel like that part's easy. This next one is the millions, and then billions is after that. So 5 billion has a 5 with 9 zeros after it. So we want to find out what that is times this to find out how much 5 billion dust particles weighs. I'm going to write my 5 billion as scientific notation. So this has 9 zeros following after it. So I know since there are 9 zeros, it's going to multiply times 10 to the 9th. And now we're going to multiply. Just like we did with division, we can choose to multiply, because multiplication is commutative. We're going to multiply the numbers together in one part, and then we're going to multiply the powers of 10 together in the other, and then multiply them all together at the end, but it'll be pretty easy. So 5 times 7.5, I don't know off the top of my head, come over here. 5 times 7.53, 37.65. So 37.65, that's the numbers part, that's what that equals. Now I'm going to multiply my reds together, 10 to the 9th times 10 to the negative 10th. When I multiply, I add the exponents. So 9 plus negative 10 equals 10 to the negative first. Since there are more negatives when you're adding, we end up having just one of them. And our positives and negatives cancel out. So now I'm going to find out what my end result is. I'm going to move my decimal place one place, and it's times 10. So I'm going to move it, it's not times 10. It's one place and it's negative. So I'm going to move it to the left because that will make the number smaller. So that's my final answer. This was supposed to be the weight, and it was originally measured in kilograms. So 5 billion dust particles at least of this particular brand of dust particles, I guess, weigh 3.765 kilograms. Now, I would recommend if you find that you have to round your numbers, please round them at least to the nearest hundredth. That's 2 decimal places. And good luck.